Welcome back. So last time we began our last chapter in this first part of the course, and we are going to complete this chapter today. And remember, the idea was that we are able to, so the idea was to start to devise a theoretical framework that is suitable to investigate rare transitions. And we started off from noting that perhaps Boltzmann theory of ensembles, equilibrium ensembles, even if this transition occur at equilibrium, meaning you have a system that performs ergodic explorations and transitions. So this is a completely microscopically reversible dynamics. Even if the dynamics takes place in equilibrium conditions, Boltzmann theory is not well equipped to describe this process. And the reason for that is that in Boltzmann theory, the information about the transition region is exponentially small and killed and overwhelmed by the information about the population in the basins. And this is simply because the population in the basins is given by the Boltzmann distribution in units of beta. And therefore, if you have, by definition, if you have a region with large free energy, then of course, a low free energy, then of course it has exponentially large population relative to the region of low free energy where a population is exponentially small. So no observable that you can predict in Boltzmann theory will ever be sensitive to whatever happens during rare transitions. So this is not the right theory to define that. And so we have to take a same approach, but modified in such a way to focus exclusively on the reactive part of the dynamics without wasting information into what happens inside the basins. And in order to achieve this result, we began our journey into what is called transition path theory. And in transition path theory, the onset is very similar to that of Boltzmann theory. We assume ergodicity. And after we assume ergodicity, we nevertheless consider only the so-called transition path ensemble. What is transition path ensemble? Now, we went through the mathematical definition last lecture, but let's not worry about the mathematical definition. We imagine we have a long ergodic trajectory, and this ergodic trajectory performs most of its time exploring the reactant and the product. But occasionally, there are trajectories that leave the reactant and reach the product before re-entering in the reactant. So, like we said last time, this would not be a reactive trajectory because it leaves the reactant, but re-enters the reactant before touching the hypersurface that surrounds the product state. In contrast, this trajectory is one that leaves the reactant and crosses the hypersurface that surrounds the hypersurface dp that surrounds the product before touching the hypersurface that surrounds the reactant. And so a trajectory is said to be reactive at time t if the next time it will reach the product will be before the previous time that has reached the reactant. So we had this mathematical definition that basically defined the concept of being in the middle of the reactive trajectory. And then if you chop off all the reactive trajectories out of the long ergodic trajectory, so basically we are interested in processes that only go from reactant to product, not from product to reactant in this particular definition. Like I said, this is a conventional thing because by macroscopic reversibility, we could also equivalently formulate the theory in terms of reactive process without distinguishing those that go from reactant to product from those that go from product to reactant. But let's not worry about this. So let's keep consistently a definition which the transition path ensemble is made by transitions that go from reactant to product, therefore, in this specific order. If you chop off and you only include the reactive part of the dynamics, you form an ensemble of short trajectories, which are locally, or if you gather them together, you get a time series of events that is only locally continuous. Because, this is time, this is the ensemble of reaction trajectory, cut it together and paste it together into a single trajectory. And of course, the trajectory is not going to be continuum. At the end of each transition segment, jump into the beginning on the next. So you can view this as a long reactive trajectory, or better, see this as an ensemble of shorter trajectories. Of course, the physics content is going to be unchanged. And we define this the transition path ensemble. And the idea is that we will perform averages over the transition path ensemble. And the basic idea would be define time averages over the transition path ensemble, and then associate these time averages to phase space averages over precise distributions to be determined. Okay. And in order to do that, we will basically follow the same program of the Boltzmann-Gibbs theory of ensemble, where you start from a concept of time averages, and then you assume the ergodic assumptions that allow you to replace time averages with phase space averages, right? So that's the scheme. But in order to fulfill the scheme, we need one central pivotal concept that is completely new to statistical mechanics relative to the old theory by Gibbs and company, and is the concept of commuter function. So the commuter function is a probability field, meaning it's a function of configuration space, and it's a probability. And I want to emphasize this. It's not a probability density. So the commuter function actually belongs to the interval 0, 1. And it's the probability that I start a Markovian process for point X in the transition region. So let's define the transition region omega t like the configuration space modulus the reactant united with a product that is the complementary in the configuration space to the reactant and product together. And that's exactly what you would expect the transition region is, right? Of course, the transition region also contains parts that are basically never explored, neither by transition pathways. For example, if I were to draw this somehow, all this part here and probably here will belong to high mountains that are never explored by transition pathways. Fine. We will not worry because they will never be explored in equilibrium, and they will never be explored by transition pathways. Basically, they are never being explored. So the fact that we include it in the transition region basically bears no effect on whatsoever statistics. Okay. Very well then. And then we define the commuter function. And we define the commuter function in terms of a concept that we introduced. There was the concept of first passage time distribution. So basically, the first passage time distribution across a surface P, so at time t, is the is the distribution of time at which a trajectory initiated at xi, or let's say x, reaches the border of P for the first time at time t. So qualitatively, we expect transition time distribution to be Poissonian-like. The probability if X is at a finite distance from the border of P, then the probability for X to reach P immediately after starting off the dynamics is obviously 0 because you have to diffuse a long way before you reach P. But sooner or later, because of ergodicity, you'll get there, right? And therefore, that's the shape of the transition first passage time distribution. But we were interested in a slightly modified concept of first passage time distribution, which is one in which I'm also including the condition to have an absorbing boundary condition at the surface of the reactant, which means that our Green's functions that we have used to compute these first passage time distributions will be 0. It will be the sum of all transition pathways from X to X final in time t that do not touch neither P nor R. Remember that. So in the path integral, we included a term that would kill the path if the path was touching delta R. Now, clearly, if you start from X and you ask, what is the probability to reach for the first time at some time t, the product without touching the reactant, and I integrate over the time, I'm asking the probability of reaching the product before the reactant. And that's, if you want, is a constructive representation of the commuter function, which is, again, the flux over the border of the product. Okay, now that's the mathematical definition. The integral over dt of the first passage time distribution across the product at time t starting from X. And now what we were able to do last time with a mathematical calculation was actually to show that this was the limit for t going to infinity of the first passage time distribution at time infinity negative the first passage time distribution at time 0. And for the reasons that I just discussed, the Poisson-like behavior of this distribution, this was, sorry, let me be more precise. What we discussed last time was that if you apply the backward Kolmogorov operator to the commuter function, we worked out a mathematical equation that related this term on the left-hand side to the difference of the first passage time distribution at infinity and at 0. And this is basically 0 minus 0. So our final result was to show that the commuter function obeys the stationary backward Kolmogorov equation with boundary conditions, with specific boundary condition. Q at the boundary of the reactant is 0, Q at the boundary of the product is 1. So that was the summary of last lecture, if you want. You might have realized I begin every lecture by summarizing the previous one in 10 minutes. And I think it's important for you to sort of keep up on where we are going. Very good. So we have this relationship and which we could solve for the one-dimensional case and get a closed expression for the commuter in one dimension. And so before moving forward in transition path sampling, transition path theory, let us sort of comment a little bit on what we expect this function to be. Well, you can solve this analytically, for instance, for a simple model for transition. in which you sort of have a double well, and then you approximate this transition region, for instance, with a parabola. Now, again, how do you do that? Remember, we have, this is the backward Kolmogorov equation in units of beta. So I'm going to write it this way. And U is an inverted parabola. So U prime is negative 2k, or let's put a half here. So this 2 goes away, negative kx. And therefore you can solve the exercise, solve for yourself, and get the commuter in terms of an integral between, say, a configuration xc and some configuration x by basically solving this equation. I leave it to you. And in general, when you have a system like this, the commuter function is 0. It grows across the barrier, and you will discover that you can actually show that in the parabolic case, this is actually a line. So if the system is at least parabolic by Taylor expansion in the vicinity of this point, it would be nearly constant here as a function of x, right? And then as you enter, the state will become stationary. So there is, of course, a point where you hit probability 1/2, which is actually this point, or exponentially close to this point. So if you start a trajectory from this point, you have 50% probability to go to the reactant before the product. And what happens if the commuter, if the energy landscape has additional minima? For instance, let's consider the example in which my potential energy is something like this. And this is my reactant, and this is my product, and there's a state in between. Well, I think now you don't have an analytic solution, but you can put this on a computer that does it very simply. But the point that I want to manage to show to you is that if I look at this equation, from this equation, I will get that d by dx of log q prime is of the order of u prime So basically, this equation is telling me that in the region where the potential is stationary, the commuter is exponentially flat, right? And which basically tells me that in this case, I have something like this. And physically, if you think about it, it makes sense, because if I have 2 points here, what is the probability that these 2 points will make it to the right and to the left? The temperature is here. they're going to diffuse to one another very fast. Basically, there is no distinction between those points in terms of stochastic dynamics. They are within a valley because they are kinetically very close. Remember the notion of diffusion distance. So when two points are very close in diffusion space, in diffusion metrics, clearly they have very similar commuter function. So they both have, in this case, roughly 1/2 probability if these two barriers are the same. Of course, when this barrier lowers, then this line rises. Because, you know, if one of the two barriers is lower, you're more likely to go here. So this example shows you that the commuter function is a highly non-local function of the energy landscape, because the probability that you're going to make it to the final state depends very much on the structure of some barrier that is very far from the point where you are, right? Because if I have to go from Trento to Riva and I'm sitting in Povo, of course, the probability that I will go to, say, sorry, that's another good example because I have to cross Trento from Povo. Say I'm staying in Sardinia, right? And the probability that from Sardinia I make it to Riva before I go to Trento depends very much on the height of the peak across the Bondone Street, right? Which is not in Sardinia, it's somewhere else. So the commuter function, like all solutions of partial differential equations with boundary conditions, are nonlinear function of the force fields because they are global functions. Okay? There is one more observation that I want to make concerning the commuter function, and it's the following. Using the commuter function, I can always perform a foliation of configuration space. You should be familiar with the notion of foliation for your analytical mechanics or differential geometry. But basically, in an intuitive way, in this 2D sketch, I can always split my configuration space in isocommuter hypersurfaces. And the isocommuter hypersurfaces will never cross to each other, because if two isocommuter hypersurfaces would cross, then of course you wouldn't know what is the probability for this point, because it belongs to two different isocommuter, right? So since the isocommuter surface never cross, they perform a foliation. Now, if you perform a foliation, then from the discussions we just had, we understood that Markov state, remember the Markov states we introduced for Markov state models? In a multidimensional configuration space, they have a very special topology. They are pancakes. They are flat, exponentially flat in the isocommuter, around isocommuter surfaces, because all points into the states must have exponentially small differences in commuter functions. We just discussed that in the previous example, remember here. So in configuration space, Markov states are pancakes on isocommuter functions. Well, of course, this picture is basically true. You know, you see the structure of pancakes only when you discretize the space in terms of equal isocommuter steps, right? Because if I have a discretized space in equal x or y, I will only see that the commuter is very slowly varying inside the states, and the states will remain of their size. So this is more like a cartoon that tells you that basically Markov states are lying on quasi-isocommuter surfaces. Okay? So you begin to understand that the concept of committer is actually important because it tells us highly non-trivial properties of complex systems. And today we will make the final step into understanding how central this concept is for transition path theory. But in order to do that, we need to introduce two more stochastic descriptors that are needed in order to describe reactive events. In Boltzmann theory, there's only one stochastic descriptor, and that's the Boltzmann distribution. In reactive theories, in transition path theory, there is the committer field and two more objects. So what are these two more objects? Well, the first questions we may ask is, what is the probability to observe the system at configuration X conditioned that X lies on a transition path? So what is the probability that a transition path visits S? Not just any path, only the transition path. Okay? Now, to answer this question in a formal way, we need to do exactly what Boltzmann was doing. We need to introduce a phase-space distribution that associate this probability, basically that allows you to compute time averages over reactive pathways. So what is the definition that will ultimately yield this probability? Well, we consider the same ideas of Boltzmann theory of ensemble. Suppose we want to compute a time average of an observable F. Okay? Because again, in Boltzmann theory of ensemble, you start from time averages because that's what you measure. Remember, I don't know, familiar, how deep you went into your thinking about statistical mechanics, but all of statistical mechanics must start from time averages. You never measure in an experiment a phase-space distribution because you never have copy of your system and make parallel calculations of the different copies of your systems. You have a system, one system, and you perform measurement for a certain time, right? But the strength and the power of Gibbs' theory of ensemble is that by introducing this super seminal concept of ensemble, you are able to replace this as a probability density in some static phase space, and you have removed time altogether. So now let's copy this idea. We say, okay, the limit, the time goes to infinity. And now I'm doing a time average over time t of my observable f of x of tau. And of course, eventually, I will have to normalize. So let me just normalize already, since I will have to do it anyway. Now, what am I average of? I'm not averaging over all transition pathways, all the ergodic trajectory. If this was the only thing I was doing, this would be the equilibrium distribution of the expectation value at equilibrium of f, because x is an ergodic trajectory, right? So if I stop here, I get Gibbs theories of ensemble, Gibbs Boltzmann theory, right? Now I'm gonna put more constraint. The first constraint that I put is a characteristic function of the transition region. So by doing this, I'm only computing contributions to the average when the trajectory happens to visit the transition region, because this is the characteristic function that is 0 in the reactant and the product. So I'm counting the time only when I'm in the transition region, and I'm performing the averaging only when I'm in the transition region. Okay? But now, of course, this is not enough. I also have to include that this is not in the transition region because of a fluctuation that will return to the reactant, like in this sketch here. It's in the transition region because it sits on the transition path. And in order to do that, I compute the position of the next time when I will leave the transition state, remember transition region, right? Remember, T plus is the closest time in the future where I will be leaving the transition region, right? And I impose to be in the product, characteristic function of the product. By doing this, I'm basically implementing this condition. The next time I will leave the transition region, I will be in the product state. Okay? So let me put it here. Next time, starting from tau, that I will leave the transition region, my position will be in the product state. And then, of course, I want to do the same, saying that the last time that I left, the time that when I entered the transition state, I was in the reactant. So I have to put here, sorry if I don't have room, I put a function here, and let me say what I'm putting here. I'm putting, guess what? The characteristic function of the reactant calculated in the position of the last time that I left the reactant or the product. So by doing this, I'm restricting the time averages to the time averages in the transition path ensemble. Okay? Now, the whole idea is that now I use ergodicity and I say, I assume by ergodicity that I can replace this time series with a phase space series over specific distributions that defines the copies of the ensemble, right? So I'm basically saying this is equal to f of x times some transition path density distributions, m of t. And this is a definition of the transition path distribution. I find this particularly elegant, but what is more elegant is what comes next. You can compute analytically MT. Because if you think about it, this is the probability to visit X conditioned to be in a transition path. But since these are, uncorrelated properties that I'm asking, I can compute the probability to be on X without conditions. I'm using Bayes' theorem if you want. And I'm multiplying by the probability that I am reactive in X. That is Q of X and the backward committer. Remember, this is the probability, the condition that X sits on the reactive pathway, because basically the probability that from X to make it to the final state is Q of X, and the probability that from X I make it to the reactant state is 1 minus Q of X, and by microscopic reversibility, Q plus Q minus is actually the probability that X sits on a reactive pathway. Okay? So as you can see, and of course there's a normalization here, which is not the Boltzmann normalization because the Z prime is defined as the integral over the transition region of M of T of X. So basically, what we learned here is that if you know the committer, this probability is you can get this from Boltzmann with the only extra ingredient of the committer. Now, why is this any relevant? It is relevant because it teaches something extremely important about the committer function again. So let's make an observation. MT of X is Boltzmann distribution along isocommitter surface. So what does that mean? I have my reactant, have my product, have an isosommeter surface, which I don't know what is its shape because it's determined in a non-trivial way by the underlying energy landscape. And then I have a number of reactive processes. Each reactive process pinches the isocommitter surface in a point, right? And I can build a distribution. Some regions will be more pinched than others, right? And therefore, what I can do, I can build a equilibrium distribution. I can build a distribution of points which are pinched by trajectory, reactive trajectories on an isocommitter surface, right? But if I look, all these points obviously belong to the transition path ensemble by construction, because these are points belonging to reactive trajectories, right? So if I compute M of T of X restricted to a isocommitter surfaces, say Q of X equal to Q bar, what I will get, it will be Q bar 1 minus Q bar E minus beta U of X times a constant. So while this probability of finding a position of next of the transition path visiting X is not Boltzmann, along an isocommitter surface, it's Boltzmannian. It reduces to the Boltzmann distribution only along fixed isocommitter surfaces. You need some kind of effort to visualize this, okay? Why should I ever care? Because you see, there is a fundamental reason, because this equation solved and sorted a problem that was in the mind. I think this equation is 2007 or 6. This problem sorted a question that was in the mind of physical chemists since the 30s. And the question that this equation solved was, what is the ideal reaction coordinate? Now, remember, the idea of reaction coordinate we discussed was very intuitive, and people in physics and chemistry and statistical mechanics weren't even quite sure on how to define this concept. They knew more or less what we were talking about, but they couldn't provide a very thorough definition of it, a solid definition that would sort of survive the ages, that would be undisputable. Now, remember, what is a reaction coordinate? A reaction coordinate, first of all, has to be a one-dimensional manifold that tells you how the reaction goes, right? But first of all, a reaction coordinate should not be a function only on the most probable path. First of all, because it should not be defined only on the most probable path, because there might be many most probable paths, many ways you go from Rome to Milan, and you want to define a function that is a function of configuration space, right? But the idea of reaction coordinate was something that was describing the reaction. So it must have been an order parameter. So it must have distinguished the reactant from the product. So the reaction coordinate in the reactant must have been different from the reaction product coordinate in the product. And there has to be a monotonical increasing function going from R to P. That was the first request, right? And the second constraint is that it has to be the slowest possible variable in the system. Because remember, when we define the potential of mean force, we want something that everything thermalizes with respect to it. So that if I set a fixed reaction coordinate, all the perpendicular degrees of freedom to this reaction coordinate in configuration space must be instantaneously thermalized. Okay? So that if I move along this reaction coordinate, I really see the rare events happening irregardless of what's happening outside in the remaining degrees of freedom. Now, it turns out that this equation provides you exactly with these properties, because the committer function is obviously the ideal reaction coordinate. Because first of all, it's a function of configuration space. It is clearly distinguishing reactant and product, going from 0 to 1 in the reactant and product. But most importantly, in the direction orthogonal to the committer function, locally and globally in the manifold of isocommitter surfaces, we are guaranteed that you're Boltzmann, you are equilibrated, because the probability of transition pathways along a isocommitter surface is by definition distributed according to Boltzmann. So yeah, we finally have, after 70 or plus years of endless conferences addressing the question, what is the reaction coordinate? This problem was sorted. The best one-dimensional description of a reaction is provided by the foliation with respect to committer function, which means that if I can take the gradient, have a clear idea how you go to if you're in that space, in which direction you go to get to the product space. So nothing in physics ever leads to a free lunch. Why? Well, you remember, in order to compute h, the commuter function, you have to solve the backward Kolmogorov equation, right? And that's the adjoint of the Fokker-Planck equation. So you have to find a stationary solution of the backward Kolmogorov equation with non-trivial boundary conditions. And that's basically as hard as solving the dynamics, because solving the dynamics is solving the Fokker-Planck equation, right? So yes, you have a collection, you have an ideal reaction coordinate, but the fact that you have it doesn't mean you can compute it easily. But at least you have a formal definition and a set of equations that you can use and maybe devise approximations that allow you to get a good or reliable estimate of the commuter functions. So you can, for instance, one of my students is building a variational calculation of the commuter function based on yet one more Ritz variational principle you can build, which involves the commuter. And therefore you have a variational guess, and then there are functions that you think they might be commuter related, and then you perform the variation in the variational space parameter, and the best solution you get is your best estimate of the commuter function. Finally, you can do things like this if you have a goal, a specific goal. So although this results is purely theoretical at this level, it's powerful enough to pave the way to approximations. And that's where physics starts, always. Once you've written the Schrodinger equation, you can solve the Schrodinger equation for an arbitrary problem, but you can devise a Ritz variational principle, and then ultimately, using Ritz variational principle, of course, you can solve the problem variationally. Just to give an example, okay? And Hartree-Fock or Hartree is a variational approximation. Density functional theory is a variational approximation. And pretty much everything except quantum Monte Carlo is a variational approximation or correction thereby, okay? In quantum many-body problems. So, okay, I think I conveyed to you the importance of this. And I want to define the last stochastic descriptor. And I want to show you, I want to start from the observation of the fact that the commuter function is an ideal reaction coordinate. We immediately pose a related question. How do successful reactive events look like? What do successful So I'm trying to, so the reason we need another stochastic descriptor is that we want to understand where the flux of probability current is large. Okay, so this is a concept that needs some thinking. Once again, reactant, product. But now let's complicate the problem. Let's suppose there is an intermediate. And let's suppose there is something we call a trap. And I can provide you thousands of examples like this in nature. The most famous one is, say, you now understand that I always use the same example, but never mind. You have a protein that wants to fold. This is my protein. Look in the screen. And maybe the protein needs to form this contact. This is the final state of the protein. But the protein, by some reason, by entropy reason, first, the terminal forms, it can happen that it forms a bond with an inner residue. Clearly, from here, you cannot simply finish the folding, because in the native state, this point here is not in contact with this residue here, is in contact with this residue here. Okay? Do you see this? So clearly, when you form this bond, in order to make it to the final state, you need to break this bond and continue. Now, clearly, the number of bonds you can form is a bit larger than the correct number of bonds, right? So by entropy, you continuously make mistake. And this is the reason why the typical timescales for local motion in proteins is the nanoseconds, and protein can fold from seconds to minutes. So count how many orders of magnitude you have there, 9 to 10, 11, 12. Okay. And the reason it takes so long is most of the time you do something wrong, you have to go back and correct. So now it's more or less like if you're typing on your keyboard randomly and you want to reproduce some poem, and anytime by random you type a wrong letter, then you have to wait until by random you type the delete button in order to go on. Right? So it's a long stochastic process. That's the essence of rare events. So most of the time, I get into traps. And if from the traps, if I happen to go from, say, the reactant to the intermediate state and from the intermediate state to the trap, then in order to successfully complete, I need to go back and continue. Because there is no path that leads me directly from a trap to the product. If there was a path, this would be just an alternative reaction pathways. So let's distinguish this from this situation in which I go from I to I prime, but from I prime, I can go directly to P. This is not a trap. This is just a secondary pathway, right? And which one is most probable will depend on how much flux do I have here with respect to flux that I have here, right? Do you agree? So the transition path density will not distinguish between these two. Actually, probably if the trap is sufficiently deep, it will be largest in the trap because you are in the reactive pathways and I only count the probability of finding the system in any of these states. And it could be very much, it could very well be the probability is even largest in T. If T is a very deep minimum, though you happen to fall into the hole, you stay there until you get the right flotation to get out, right? So if I only look at the probability density, I will never know how to distinguish a trap from an on-pathway intermediate. So this is called off-pathway, and this is on-path. Okay? Clearly, all I need to do to distinguish is to measure the flux of reaction pathways across hypersurfaces that embody, that separate, say, I from I prime or I from T. Because if this is a trap, the flux of reactive pathways will be zero across the hypersurface. Okay? And the flux is the flux of a transition path current, of a current that I can construct out of transition pathways. Okay? Now, the definition of this current, now I spent some time in giving you the physics of it because the mathematics is not very complicated, but it's not as simple. as in the transition path density, but let's spit out the definition, and then you'll discover immediately that it makes sense. Okay, so I want to define a time average and then replace it with a vector distribution in configuration space. This vector distribution would be the current, okay? Okay, so I take the limit from t going to infinity. Now, 1 over TTP, this is TTP is the sum of the transition path. Remember, with the h's plus, h's minus, h's omega that I introduced before, okay? And by these h's, I mean simply the h's of transition, blah, blah. Okay, fine. Now, what I do more, what I do in addition to what we were doing before is that I have a reactant, have a product, and now I introduce a dividing surface. And now we call this portion of configuration space S, and this portion is going to be omega t modulus S. It's a dividing surface, so I can do that because it divides into configuration space. So what do? Actually, sorry, let's do the opposite. It's a bit easier to do it this way. So I want to measure the flux of the transition path through this surface, okay? How do? I look at the path that at some time t belong to the region S, H, S, X of tau. And I only consider the paths that after time delta t cross the surface. So multiply by H omega t modulus S, which is this region. Let me call it S prime, not to have to carry around omegas and S's. Okay? So S prime is omega t modulus S. So I'm saying the configuration after time t plus delta t is on the other side. But since this is a flux, I also have to subtract in this definition the paths that cross in the opposite direction, right? Because I'm interested in defining a current that will ultimately define a flux, okay? So here I'm computing the flux, and I want to associate this flux to a current integral, okay? So I have to take away h of S prime of x of tau, h of S x tau plus delta t. Okay, I write it here. So clearly, if in my time delta t, I go from here to here, I will satisfy this h, this h, this h, but will not satisfy any of this inside the brackets, because this is a double request to be on this side before and on this side after, and to be on this side after, before, and on this side after. So I will not cross the surface. This square is this round bracket only selects out the paths, the trajectories that in an infinitesimal time delta t will cross the surface, right? And of course, I want to take the limit for delta t that goes to 0 and from t that goes to infinity. Now, this is my time average. And the idea that I've identified this time average with the flux across the surface of S of a current. And I will define this to be my transition path current. Okay. Now, just like in the case of the transition path density, it turns out that you can write the transition path current once you know the committer and the Boltzmann distribution. And this is where I'm not going to provide a proof because it's a bit cumbersome. You find it in the references if you are interested in that I've put on my notes. But I don't want to bother you with 2 hours of proof, okay? But it turns out that this is actually the gradient of the committer times the Boltzmann distribution with a diffusion factor, diffusion coefficient on front that provides the time scale. So the productive pathways basically follow the gradient of the committer, which is, again, the proof that the committer is the ideal reaction coordinate. And I think you should appreciate how elegant this is. It really looks like we found the right way of phrasing the problem because things fall together very nicely. With this extra concept of committer function, then all of a sudden you're describing time-dependent processes through time-independent distribution. Let me repeat this. You're describing time-dependent processes, transition events that they're associated with a rate. They have intrinsic dynamics built in. So this is dynamics. However, times has disappeared because I have a scalar, a probability field, a scalar distribution, and a density and a vector distributions. All of them are time independent. Because if you want, they correspond to stationary distributions of a non-equilibrium process in which I continuously emit trajectories from the reactant and I absorb them when they enter the product. So it's basically like when you wash your hands in the morning, switch on your tap water. There's a short transient, which is the time it takes for the first time to the water to cross your trajectory to the sink. But after, say, a fraction of a second, you have a stationary distribution. There is time independent. That stationary distribution, however, describes a non-equilibrium process, a dynamical process. So similarly, these stationary stochastic descriptors describe reactive events. So in the past years, I think it's the 3rd year that I give these lectures on transition path theory. And some problem that the students had in the previous years when they were giving me their feedbacks was that, okay, that is very nice, but they couldn't grasp how to make use of all this, to see it in action. What do I use it for? Now that I know that the reacting current is, then how do I ever worry about that in my practical life, right? You might ask the same question for the Gibbs distribution. But now let me ask you, why is the Boltzmann distribution such a useful concept in practice? In practice, meaning when you need to make contact with experiments. That's my working definition of practice. And if you cannot make contact with experiment, everything we say goes into the garbage can for physics, because it's not physics, right? If you cannot validate it, it isn't physics. You don't have to be validating it today. You might have to wait until you can validate it to put it into a Hall of Fame of physics, but it must be something you can validate. So let me ask you, when does the Boltzmann distribution become practical? Why do we think the Boltzmann distribution is such an important concept? And we all agree, right? The Boltzmann distribution is pivotal. Let's remain in classical mechanics, okay? Do you have an idea? Well, for instance, because you can devise algorithms that efficiently sample the Boltzmann distribution in certain cases, even if they are not physical. Give me an example, if you know, of an algorithm that doesn't correspond to any physical dynamics, yet samples the Boltzmann distribution. Do you know? Have you done any computational physics in your background? Anybody?
Yes, like Metropolis.
Metropolis. Now, for those who haven't, don't worry. You will, if you will stick, for instance, if you will take a molecular simulation course next year, they will give you that too. However, the Metropolis algorithm is an efficient way to sample directly the Boltzmann distribution without having to follow the dynamics, because the alternative is to integrate the equations of motion for a very long time, but that, guys, is performing the time average after all. Right? It's not going to the ensemble, it's to stay at the starting line and do the definition of time average. You're really using the theory of the ensemble when you have a smart way to get directly the phase space distribution and average over that through the central limit theorem, right? And there are algorithms that you can demonstrate that are better convergent than the physical dynamics, and yet sample the correct distribution. Now, it so turns out that you can devise algorithms. Actually, we were the one to demonstrate this and to devise them, but in my team. But it turns out that you can do the same with transition path sampling. You can devise fast algorithms, smart algorithms that by construction lead to the correct transition path theory distributions, although they are non-physical. However, with a big however, in case of Metropolis Monte Carlo, you don't have to do nothing to the system. You just have to do acceptance and rejection. But in the case of transition path sampling, you need to have a proxy of the committer to push the system. So in other words, you want to define dynamics that pushes the system fast, accelerate the system by pushing in the director of the committer. And if you know the committer, then of course you can sample the Boltzmann distribution. You can get the rest of the information out. Of course, you don't know the committer. So these methods, unlike the Metropolis Monte Carlo, are only useful in a variational sense, that you have a good approximation or good proxy of the committer and you use it. However, by doing that, we were able to reproduce the same results of molecular dynamic simulation for protein folding to a statistically indistinguishable difference from the only protein. So basically, just to give you an idea, there's only one supercomputer that can solve protein folding simulation by MD. It's designed to do only MD simulations. So all the algorithms are on chip. And using that in 2010, they could fold sub-millisecond protein folding, meaning those 10, 15 proteins that fold in super short times. But in order to fold the biologically relevant proteins, forget it, because in order to do that, you would probably need, we estimated that to fold a protein like a serpent protein that I will show you a movie, it will take you some 300,000 years of simulations on that supercomputer. Okay, so biology is still far away. However, if you are ready to pay the price to do variational calculations, you can first check how good you are by comparing your results for the same system, same model with the real molecular dynamic simulations. And what we found was complete agreement, indistinguishable from the study. And then using these algorithms, we could go from, say, any time between milliseconds to minutes. And maybe I could stop here my sharing to give an idea. Okay, let's share it from here. I want to show you a movie just to rest a little bit. Let's say. Yeah, for instance, this. This is a protein that I'm going to show you. It's a simulation